Okay, good morning, everybody. You should have your notes open up to page 20. If you have your textbook, in about 10 minutes, we're going to be working from page 251, the practice questions, so you can turn to those now, save you some time. And you'll need your data booklet for today's lesson as well. So if you haven't taken those things out, your sub's going to pause the video and you're going to do that now. Okay, so today we're going to be talking about Arrhenius acids and Arrhenius bases. So up to this point, we've said that if you have an H in the formula and the state is AQ, we know that it's an acid. And if we have an OH in the formula and the state is AQ, that it's a base. And this works for about 90% of the chemicals that will be given to you, but there's some that really don't make any sense. So for example, if we look at ammonia, ammonia is NH3. According to that theory, ammonia would actually be an acid. However, as we're going to talk about today, ammonia is actually a base. And we're going to look at why that is today. Okay. So your first blank is acids, next blank is bases. So Arrhenius developed a theory to explain acids and bases depending on the content of your hydrogen ions, H+, and your hydroxide ions. So up until this point, if I asked you to prove why sodium hydroxide was a base, you could write a dissociation equation. Remember, when we're writing dissociation and ionization equations, we should write that over the arrow. Okay, so if sodium hydroxide dissociates, it's going to break apart into sodium ions and hydroxide ions. Okay, it should be balanced, which it is. So what we would say is that this ends up making a basic solution because the OH ions floating around make it a base. Those OH ions will react with litmus paper. Those OH ions have a chemical property that they actually feel slippery, so that's what gives a base its properties. And then we can say the same thing with acids as well. So if we look at hydrochloric acid, for example, remember acids ionize, which would mean it would break apart into H positive ions and chlorine ions. Again, this ends up being balanced, so we're good. And again, we would end up explaining that the reason why this is acidic is because your H ions are floating around. Now, a little confusing because we've been talking about this hydronium, but we really haven't come back to this. So we know what's actually going to happen is this H is going to react with water to make hydronium, because remember, H is actually unstable whether it's an ion or whether it's just by itself, and so it always wants to find a buddy, so it's going to pair up with water to make H3O, but we'll come back to that in just a second. Okay, let's look at one last one. So sulfuric acid, same thing. We can write the ionization equation for sulfuric acid. We say that it ionizes, which means it's going to break apart into hydrogen ions, sulfate ions. Okay, and remember, if you can't remember your charges, you just look them up in your periodic table. I just use these all the time, so I've memorized the charges. Okay, and same thing again. That H is going to make it acidic. And my mistake, that's actually going to be HSO4. Sorry. Okay, so what's actually going to happen is this HSO4 is actually going to ionize again. We're actually going to come back to that and talk about that in Monday's class, about when it ionizes again, what that actually means in terms of solutions. Okay, so that's Arrhenius's definition of an acid, that if it's got H positive ions, those floating around in solution make something acidic. If it has OH negative ions, hydroxide, that floating around makes the solution basic. And then again, that works for most of the substances, and that's the Arrhenius definition. But today we're going to look at the revised definition because, again, it doesn't hold true for absolutely every compound, like your two I have listed below. Next blank should be chemicals. So, for example, magnesium oxide. Arrhenius would have, based on the principle that H's make it acidic, OHs make it basic. He would have actually predicted that magnesium oxide should be neutral because it doesn't end up having an H in it or an OH. Let's write that down. M magnesium oxide, he predicted that it would be neutral because it was missing H positive or OH negative in the formula. And then same thing with your ammonia. He would have predicted, and be careful with ammonia. Remember, we have ammonia and we have ammonium. Both end up being basic, but ammonia is NH3, ammonium is a polyatomic ion, NH4 positive. Okay, so either way, he predicted that it would be an acid because of the H positive in the formula. And as you'll see in just a moment, both were proven wrong. That's the focus for today. Why is that wrong? Okay, so both failed to produce a neutral or acidic solutions as Arrhenius' definition would have predicted. So now we're going to look at the modified definition of Arrhenius. So the prediction of acids and bases on the principle of collisions with water particles is actually a better predictor if something's going to be an acid or base. So not just looking at H, not just looking at OH, but taking the whole compound and look at how it reacts with water. So we know that H positive ions are unstable. They're not likely to exist as just H positive. They're going to form with water to make hydronium, that H3O. And so we've written this formula down before. We have H positive ions, react that with water, and we get hydronium. Okay. And so I keep getting you to write that down. You're going to write it down at least a couple more times. Your next in-class assignment, your unit exam, when I ask you to explain how hydronium ions are formed. So they're formed because H reacts with water. So in general, acidic solutions are formed when substances react with water to form hydronium ions. Now here's where we need to be careful, because if I ask you to prove something is acidic based on Arrhenius' definition, you can just say there's an H in it, it's AQ, it's an acid. If I say prove why something's acidic using the revised definition, that's when you react it with water. So be careful, make sure you're reading things carefully. Today's homework, it's all going to be revised, but when it comes to Monday and next week when we're reviewing the whole chapter, you have to be very careful that you're looking for original or modified. Original, again, is just H positive, and aqueous makes it acidic. Revised is when it reacts with water. So let's look at our same formula, and let's actually, we said that hydrochloric acid is acidic because of the H and because of the AQ. But let's react it with water and look at this revised definition. Okay, so we're going to react it with water. We're not going to ionize it to prove this. We're reacting it with water, so we don't write anything over top of the arrow. And we know that this H is going to actually come and it's going to react with water, and it's going to fuse with it, and that's how we actually make that H3O. So now that makes a bit more sense. We keep talking about this H3O, but we haven't been writing it in the formula. Now, if you do that, I want you to think about this here for a second, because if you take this H out, what's left in this formula here? Just the chlorine, right? So you put that chlorine ion, and don't forget the charge. So the great thing is about these formulas that you're doing, these revised formulas for Arrhenius acids and Arrhenius bases, is you always know 75% of the question. You can always get 1.5 out of 2 on these questions because you always take the chemical they give you, hydrochloric acid. You always react it with water. Okay, so I always give you 1 mark for the left side of the equation. Okay, so that's 1 mark there just for putting those down. And then you'll always be told to prove that it's an acid or prove that it's a base, because some of the substances you could actually go either way. And so if you're told to prove that it's an acid, well, you always put your H3O first. And there you go. That's 75% of your equation that's done. And the trickiest thing is coming up with that last ion. And you do that by going back to your original equation. Okay, if you took that H and fused it with the water, okay, then that means that that chlorine is left behind. So that's how I came up with that chlorine. So that's the biggest thing that people ask me is how I came up with that last ion that's there. Okay, so let's do the same thing for sulfur dioxide. And I keep meaning to change this in my notes. This is actually a complex one that I should be looking at on Monday instead, but let's look at it anyways. So let's react it with water. And you'll see in a moment and when I work through some sample questions, anytime you react something that's an oxide, so this would be considered an oxide because it has oxygen in it, you actually always need 2 waters, or else it ends up being a little bit interesting in terms of trying to balance it. So same thing in this case here, these substances both end up being an acid, so I'd have to tell you that. If not, you could end up trying to prove that it's either. So if you're proving that it's an acid, again, your first product should be hydronium. Don't forget the charge, don't forget the state. Okay, now here's where we need to think for a bit, because we have that, we have 2 waters that are there. So if you think about this, we've got 1 H3O. Okay, so we've already accounted for 1 of the oxygens, but there's actually 2 because of the 2 that's in front of here. Okay, so we actually have 2 oxygens. We have 4 hydrogens. Okay, so we still end up having 1 hydrogen and 2 oxygens left over. So in your formula, you will end up having HSO3 negative as your final product. Okay, so these again, these are these revised formulas proving that something's an acid or a base. Okay, so that's for acids. Now let's look at an example of a base, a formula that doesn't typically look like a base. It doesn't have an OH, but still is considered basic. Okay, so the Arrhenius bases. So it can be predicted that a basic solution is formed with substances that react with water. So again, the revised definition, we're always going to react something with water. So let's come back to this ammonia, this NH3 that looks like it's an acid, and see why it actually ends up making a base. So let's add water to it because these are the revised formulas. I've asked you to prove that it's a base. Okay, so if it's a base, your first product is going to be OH. Okay, so you've done 75% of the equation. Now, I always tell students that another way to think about water is to actually write it as HOH. Because if you look at it, there's still 2 H's and there's still 1 O. It's still the same formula. But if you hate balancing equations, it makes a little bit more sense in terms of what happens and why it ends up being a double replacement reaction. So what ends up happening is if you take the OH out of this formula here, you can still see you have an H, and that's going to end up combining with the NH3 that's there. Now, remember, your H can be a positive or a negative charge. So in this case here, your ammonia is already a compound and it has no charge. But you're going to add an additional H onto it, which is actually going to end up making it positive or negative. In this case here, NH3 might look familiar. It ends up being a polyatomic ion. So it ends up having a positive charge, and it's aqueous. So again, I've proven that this is a Arrhenius base. I've used the revised definition because I've reacted it with water. You'll always be told again to prove if it's an acid or a base. So I've just said to prove that it's a base. So your first product is going to be OH. And then you got to try to figure out with that last formula and what's left over as to what your final compound will be. And again, that ends up being the trickiest. Okay, so that's the revised formula. Here you can see that there's still those OH ions floating around, and that's why this solution will be basic. It's actually quite a strong base. It's not your ammonium that's making it basic. It is contributing because this will actually react again, and we're going to use this to review on Monday. But specifically looking at this formula, this is basic because when ammonia reacts with water, OH ions are produced, okay, and those floating around give it its basic properties. So let's look at the rules that we're going to use when we're writing these equations. And I just stole them straight out of your textbook. So next page, page 21 in your notes, says that to write these formulas, you're going to write the chemical formula for each of the reactions, molecule or polyatomic ion and water. So you take whatever chemical I've given to you and you add water to it. Now, what actually needs to be done even before you start that is you need to make sure that you ionize or dissociate a chemical if it has any group 1, group 2, and this is actually a mistake in your textbook. That should be 17, not 7. Or group 17 anions in the compound formula. Evidence from many compounds show that. So for example, if you had sodium hydroxide, group 1, sodium comes from group 1. Group 1 ions have actually found to not contribute to acidic or basic properties. So we're actually going to ionize or dissociate anything that has a group 1, 2, or 17 ion in the formula because we know that that doesn't contribute to acidic or basic properties. Now, if it's a non-metal and it's an oxide, so this is what I mentioned before. So if it has an oxygen in its formula and it's all non-metals, so C is a non-metal, O is a non-metal, S is a non-metal, O is a non-metal, then you have to add, same thing, you can still go CO2 plus water, still SO2 plus water, but you have to always add 2 waters or else your formula ends up being really weird in terms of trying to balance it. You won't be able to balance it. For every mole of the substance in the reaction. And then look at the evidence provided. This is the big thing. Because really, if this wasn't the case, we'd spend a week on this of trying to figure out if it's going to be acidic or basic. But for the sake of Chemistry 20, you'll always be told if it's an acid or a base. That's that 75% of the formula that I told you you'll always have. So if the evidence tells you that it's acidic, then your first product is going to be hydronium ions. If the solution is basic, then you know that the first product is going to end up being hydroxide ions. And then the trickiest part, as I keep mentioning, is trying to figure out what that last chemical is going to be based on whichever letters are left over. Okay, so let's try some practice problems. So if you haven't opened up your textbook to page 251, do that now. And if you guys are stirring around, your sub is going to pause this video while you turn to that page. Okay, so on page 251, I'm going to do question 1 and 2. So even if you don't have your textbook, I'll read it out loud. Use the modified Arrhenius theory to suggest a chemical reaction equation to explain the acidic properties of each of the following solutions. Okay, so there's 3 formulas here. We're going to do 3 together. And again, we're told to prove that they're acidic. Now, A tells us that it's HI aqueous, so let's write that down. Okay, so it's hydroiodic acid. Okay, and again, the question tells us to prove that it's an acid. Now we're doing the modified equation, so we're always going to add water. So let's do that now, plus H2O liquid, arrow. Okay, so I've already got 1 mark out of 2 for this equation because I've got the left side done. Okay, now do I need to add 2 waters? Or can I just leave this water as itself? Okay, it should be just left as itself because there's no oxide in this formula, so I don't need to add 2 waters. Okay, so now I can go back to my right side of the equation. I've been asked to prove that it's an acid, so that should mean my first product is H3O, positive, aqueous. There we go. Okay, so now let's go back to the equation. That H3O came from water, right? There's that H2O. And I also stole that H to make that H3O. That's how I got this formula here. Okay, so that means that all I have left is that I, right? Okay, so I'm going to write down I. And anyone notice what I'm missing? Don't forget, if you break it apart, that means that you're going to end up having that negative ion. Okay, where did I get that negative charge from? I looked that up in the periodic table. If you find I, you'll see that it has a negative charge. Okay, so let's look at the next one, B. Again, you're told to use the modified Arrhenius theory to suggest a chemical reaction equation to explain the acidic properties of HOCl. Oh, I think that's chloric acid. There we go. HOCl. OCl is a polyatomic ion. Okay, so modified formula, so we're going to add water. Okay, it's not technically an oxide, even though there's that O there, and even though that H is a nonmetal, because remember, H tends to break the rules all the time. H is in group 1, and in this case here, if you actually look at the way the formula is written, it's written this way because we write it like an ionic compound, even though technically it's all nonmetals. Okay, so we're not going to react it with 2 waters. We're just going to leave it as it is. We're asked to prove that it's an acid, so that means your first product should be H3O aqueous. Okay, so there's your water. That's what made this H3O here. Okay, but that's just 2 H's in there. I need one more, so I'm going to steal this H. Okay, and then I should be left with OCl negative. Now, let's start thinking about this, because if you look at your table and you find H, number 1, you can see that in the box it says it can be positive 1 or negative 1. Okay, now, in this case here, if you find OCl in your table of polyatomic ions, it's negative 1. And since this is a compound and there's no charge on this compound here, if this is negative 1, then this would have to be positive 1. That's why it's no charge, right? Okay, so when I take a positive out, that's why that ends up being negative. Or you can always just cheat and go back and look in your periodic table, your table of polyatomic ions. That will work for you every time. Okay, last one, H3PO4. H3PO4. Phosphoric acid. Okay, so again, same thing. I'm going to add water to it because we're asked to prove using the modified formula. Okay, we're asked to prove that it's an acid, so your first product should be H3O aqueous. Okay, that H3O was made from this formula, but it still needs one more H, so I'm going to take one more H out of here. Okay, so if I take an H out of H3PO4, my question to you is, what's the formula of what's left over? Okay, not a trick question. If you take one H out, then you should have H2PO4. Okay, it's going to be aqueous. Now, charge. This is an acid, and the H in acids are going to be positively charged. So if you take a positive out of this substance, it becomes more negative, and now your H2PO4 is negatively charged. Okay, so again, that ends up being tricky. But again, if you looked, that ends up being a polyatomic ion. Okay, so those are for the acids. The acids I find much easier than the bases because you can take the formulas just as they are and add water to them. If you were asked to explain the acidic properties of any of these, and that's it. If I didn't say modified theory, you could just ionize each of those and that would work. But because I said modified, you have to react them with water. Now, bases are a bit more tricky. The only thing I'm going to add with the actual rules itself for your bases is that you need to make sure you dissociate the equation first. Okay, so number 2 reads, in case you don't have your textbook, where possible, use the modified Arrhenius theory to explain the basic properties of each of the following solutions. Include appropriate chemical reaction equations. Okay, so the first thing that I'm given is Na2SO4 aqueous. Okay, I'm asked to prove that this is a base. Now, at first glance, this does not look like a base. So if it doesn't have OH in it and you can't tell that it's a base, the very first thing that you have to do is you have to dissociate it. So I'm going to do this in 2 steps. Now we've got a really bright class, and a lot of you, I'm going to say at least half of the class, is probably going to skip this first step, which is fine. I still want you to write them down for these practice problems. So when you're doing your questions, if you can do this first step in your head, that's fine. The only problem is if you make a mistake, and your final answer ends up being wrong, you'll get no credit. Whereas if you end up putting your first step and I can see where you made your mistake, you'll still always get at least 1 out of 2. So I always suggest doing this step. Okay, so you're going to dissociate it, and if you dissociate it, you get Na positive ions, SO4 2 negative ions. Have a quick look. check to make sure that this is balanced. Okay, and there we go. Now it's balanced. Okay, now if you go back to your rules, look at your rules on the top of page 21. Okay, and remember it says write the chemical formula for the reactions. Look at that first bullet. Ignore any group 1, 2, and 17 ions. Now if you look, do either of these belong to group 1, 2, or 17? Okay, so you should notice that your Na belonged to group 1, so we're going to ignore it because through the reactions that scientists have already done, they've seen that the group 1, 2, and 17 don't contribute to something being acidic or basic. So the revised formula says just take the important ion and show that reacting. So let's do that. We have SO4. We're going to carry that forth. So here's this actual equation that's proving it. This is what I'm going to get my points for. Okay, and it's the modified formula, so I have to add water. Okay, and remember I'm proving this as a base, which means your first product should be OH. Okay, so I've gotten 1.5 out of 2 for this question so far. I need my other chemical. So remember your OH or hydronium, regardless of what it is, it always comes from your water. So if I took one O out of this formula, that's going to be gone. If I took one H out, I'm going to have one H left. So I have an H, which I'm going to pair with that. Okay, and then I'm going to have HSO4 aqueous. Okay, it kind of looks like an acid, right? Okay, and that's okay. So now what about its charge? So you got to go back to the original charge. Okay, if you look on the left side of your equation at sulfate, look at the charge is 2 negative. I added a positive H to that. So your charge should be -2 plus +1 should be -1. And there you go. Okay, so that's the revised formula. You reacted it with water, you ignored the group 1 ions, and so your mark still comes. You still get 1 mark for the left side, 1 for the right, but you had to have dissociated it first. So if you can dissociate it in your head with that first formula, that's fine. You just need to make sure that you've got the proper charge on that ion that you're carrying forward. Okay, let's try another one, B. Okay, so in B, we have NaCH3COO. Okay, so again, we've got a bright class, so I'm going to show you how I personally do these, and then I'm going to go back to doing the last one the way that I showed you how to do the first one. Okay, so again, I'm asked to prove that this is a base. So at quick glance, I'm going to double check. Is there a group 1, a group 2, or a group 17 ion? Anyone notice? Right, yeah, there's that Na. Okay, so now I have left CH3COO. Whoops, that charge shouldn't be on there. Okay, so now I have left that CH3COO. So that's actually all I need to react forward. Now, if you write it like this in the formula, I won't give you points. You have to make sure you write it nicely. So I personally would just see in my head that that Na is gone. And now I'm going to react CH3COO aqueous. Now, if I took away an Na positive, what's the charge of this going to be? If you take a positive away from the formula, that should be negative. If you're unsure, if you actually look, this is the first polyatomic ion that's listed in your table, acetate, and you could cheat and just look up the charge. Again, in Chemistry 20, that should work for like 95% of the questions I give you. You'll end up finding if it's got more than one capital letter in the formula, you're going to find it in your table of polyatomic ions. Okay, so now I can continue with my equation, and we're doing the modified theory, which means we always add water to it because we're proving that what makes it basic is how the chemical reacts with water. Okay, I'm proving that it's a base. So your OH is the first ion that you're going to write down. Okay, and now you got to figure out what's left over. Okay, so I took out from the water, I took out an O, I took out an H, I have one H left, right? And now I have CH3COOH aqueous. Now, anyone notice anything about that last chemical? Anyone notice that that's an acid? There's that COOH, an aqueous. But again, we're proving that it's a modified, this is the modified Arrhenius theory. So the modified is how it reacts with water. We can actually take this and react it one more time to prove that it can also be an acid. But at this point, we were just asked, if you actually took sodium acetate and you react it in the lab, it would prove to be a base. Okay, so this acetic acid doesn't actually break off that H in the end, and that's why it ends up being basic instead of acidic. But again, I'm going to come back to those weird ones on Monday when I'm back. Okay, so I would have dissociated it. Like I could have taken the same formula and I could have broken it down into Na positive, okay, and then CH3, COO negative, and then ignored that and then carry this one forward. But I could just see that in my head, so I just let that step out. And it's up to you. You don't have to show that first step. But again, if you would have made a mistake and you dissociated it wrong, you would get no credit for that question. Okay, last one. Okay, so SROH negative. Sorry, I don't know why I said negative. Okay, now, if you look at A and B, both of those compounds, they didn't look like bases. They didn't have OH in the formula, but this one looks like a base. You still have to react it with water. Okay, so I'm going to take this formula. Anyone notice anything about the formula? An ion that you could perhaps ignore? Okay, if you look it up, strontium is actually a group 2 ion. Okay, so in my head, again, I would just take that OH and I'd carry it forward into the next reaction, but I said I was going to do the full thing again, so let's do that. So it would break apart into strontium ions and OH ions. Okay. I'm going to ignore strontium because it's a group 1 ion, and I'm going to carry that hydroxide forward, after I balance it, of course. Okay, so now I'm going to take that OH. Whether or not you put that 2 in front for the second equation doesn't really matter. We'll get a different balanced equation, but that's okay. So we're going to take that OH ion. There we go, and that's what we're carrying forward. And I know already it looks like a base, but because you're asked to prove using the modified theory, you have to do it this way. If I just said to prove that it was a base, you could dissociate it and use that as your proof. But here you're asked to use the modified, so you have to react it with water. So let's do that. I was asked to prove that it's a base. And this one always gets people. You get one like this in your homework too, because the left side looks exactly like the right side. But let's look at this here for a quick second. Okay, so this is reacting with water, right? Okay, so one of these H's is going to fuse with this, right? And then you end up getting H2O. Why do I keep putting negative charges on everything? Let me erase that. Okay, right, so we took that H and we added it over here. And then if we did that, we'd have one O and one H left, right? And there's that OH there. So the left side and right side look the same. It looks like the weirdest formula, but again, that proves using the modified formula that that's a base. Okay, so it'll work like that every single time in this course. You'll always be told if it's a base. Now, on your unit exam, you're going to get a question where it can go either way. You could prove it as being an acid or a base, and that's fine. And the question exactly says, prove the following chemical as being a acid or a base. So you do the same thing. You start with the first chemical that you're given. You react it with water. Okay, and if you decide you want to prove it as being an acid, your first chemical in the formula is going to be H3O. If not, you're going to use OH, and then you try to figure out whatever's left off for this last one. But again, I'll do that. If you don't understand what I'm talking about, I'll do a demo question on Monday for review. Okay, so last thing. So when you're doing your homework today, make sure you're looking in their textbook, because your textbook will, sometimes they'll say, prove that it's an acid or prove that it's a base. And then sometimes they say the empirical evidence. So meaning they went to the lab, they performed the experiment. They'll say litmus paper turned blue. Okay, so you have to know that, okay, blue means a base. So they're saying prove this is a base. Or they'll say it has a pH of 2. Okay, so you have to know, okay, pH of 2, that's lower than 7. That would mean that it's an acid. Okay, so they'll give you the evidence and you have to, or they'll tell you if it's an acid or a base, and you're going to end up proving that. Okay, last concept before you start, and that's a neutralization reaction. So Science 10, we talked about neutralization reactions, that you take an acid, you take a base, put them together, they'll cancel out their acidic and basic properties, and then you end up with a neutral chemical. So according to the modified Arrhenius theory, acids produce hydronium ions in solution, and bases produce hydroxide ions in solution. Next two blanks, hydronium and hydroxide. So if we know that it's hydronium that makes it acidic and it's OH that makes it basic, then if we mix the two together, it's the way that those ions react together that end up making something neutral. So neutralization can be defined as the reaction between hydronium and hydroxide ions to produce water. Okay, so up till now, if I gave you a neutralization reaction, we could take an acid, hydrochloric acid. We could take a base, sodium hydroxide. This ends up being a double replacement reaction where hydrogen comes in here, bumps out the sodium, and then we get water. We get the Cl, which comes over here and fuses with the Na, and we get salt. Okay, so in Science 10 we said that a neutralization reaction is an acid plus a base gives you salt and water. And truly in science, salt doesn't always mean NaCl, it means anything from group 1 paired with anything from group 17. So technically lithium fluoride is a salt, potassium chloride is a salt, anything from group 1 and 17 together. Okay, so that's what we've said up till now, but if we're using the modified theory to prove that it's a neutralization reaction, we have to look at what makes it acidic. So in this hydrochloric acid, it's the hydronium. It's how that HCl reacted with water to make hydronium. In the base, yeah, you have the Na and the OH, but remember those Na ions aren't significant, so it's the OH ions reacting. And then the water is what ends up making it neutral. To get one question in today's homework, and it's very similar to this. I'll give you an acid, and I'll give you a base, or your textbook does, I should say, and they say to prove using the modified theory that this will end up being a neutralization reaction. It doesn't matter what acid I give you, what base I give you, this will always be the final answer. That's a question on your unit exam too, multiple choice. Okay, so no matter what acid and what base, if you're asked to prove using the modified formula, you just react hydronium plus OH, and you always get 2 waters. That's the formula every time, no matter what acid and what base. Okay, so I'm going to post this video online on my website, so if you need to watch it again tonight or over the weekend for homework, feel free to go ahead and do so. Your sub is going to put your homework on the board. You're going to be working on page 253, numbers 1, 2, and 4 to 6. I encourage you to work with a partner so that if you get stuck between the two of you, you guys can problem solve and figure it out, or ask another classmate. You guys are a really bright class. So get this done. If you get stumped on a question, leave it and go on to the next one. And then when I come in class on Monday, the first thing I'm going to do is take up any questions. So if we need to take 20 minutes and go over a couple questions, that's fine. But I want you to have tried these on your own. Because remember, for each of these, you should be able to at least come up with 75% of the equation on your own. Okay? So enjoy your homework, well, as much as you can enjoy homework, and have a great weekend. I'll see you guys on Monday.